Okay, so let's start today class. In the previous class, we already completed that SMES system. How can energy stored in that particular system? Okay, so today we are going to another energy storage device, like the electric and magnetic energy storage device. Okay, so today we are going to discuss electrical and magnetic energy storage device. Or under this content, we are going to discuss capacitor and inductor as the electrical energy stored in the capacitor and magnetic energy stored in the inductor. Okay. I think you are already familiar with the capacitor and inductor. So just try to explain here how can energy we can store in the form of electrical in capacitor and magnetic in inductor. So capacitor is nothing but capacitor is a storage device which can store electrical energy in between the two parallel plates separated by insulating material. Okay. So this is the systematic symbol for the capacitor. That means the two parallel plate is connected here, and this is the systematic diagram. Just the capacitor. Hello. हेलो शंकर आवाज आ रही है?
Yes, sir.
Okay. So today we are going to discuss electrical and magnetic energy storage device. Okay. So under this content, we are going to discuss capacitor and inductor. So capacitor is nothing but a energy storage device which can store electrical energy in between two parallel plates separated by an insulating material. Okay. So these are two parallel plates, and these two are separated by dielectric material. There the permittivity is represented by epsilon. This one is your positive plate, and this one is your negative plate. Okay. Positive and negative. So charge is stored in the positive here in this plate, that is represented by plus Q, and here this plate is negative charge, that is represented by minus Q. Okay. When this capacitor you connected with your battery, so electric charge, that is positive charge and negative charge, are stored in this plate and this plate respectively as positive and negative. Okay. So this is the electrical representation of the symbol of the capacitor, that is two parallel plate. So capacitance of a capacitor is defined as the what is the capacity of the charge stored per unit potential difference. Okay, so the unit of capacitor, as you know, that the farad. So either maybe microfarad or that is microfarad, that means 1 microfarad, 2 microfarad, that is 1 into, that means 10 to the power minus 6. Okay, So capacitance is represented by whatever the charge stored, that is represented by Q into per potential difference between the two plate. Okay, that is this positive plate and negative plate. So C equal to Q by V. Okay. Next is, this is the representation again here when the voltage apply across this capacitor. So the capacitor store the electrical charge between the two plates, in the positive plate and negative plate. So the unit of capacitance is already said that the capacitance value are normally such as microfarad, may be represented in microfarad, nanofarad, and picofarad. So how we can convert the microfarad, nanofarad, and picofarad in farad? These two are conducting plates, that is connected in parallel. So this is the dielectric medium of the, and charge stored in the two plate is one as a positive charge here and negative charge here. When you apply a battery across this capacitor, so electrical energy stored in the capacitor, and whenever if you require that electrical energy used, then this capacitor can be used for supply the electrical energy. Okay. So how we can convert the microfarad and nanofarad and picofarad? Capacitance value normally represented in microfarad, nanofarad, and picofarad. So how we can convert in farad? In microfarad, if you want to convert in farad, then that means 10 to the power minus 6. And what is the nanofarad? How we can convert? नैनोफैराड को हम लोग कैसे कन्वर्ट कर सकते हैं शिवशंकर
10 to the power minus 6
नैनोफैराड को microfarad can convert it into farad by multiplying 10 to the power minus 6, not nanofarad. Okay. So how we can convert the nanofarad?
10 to the power minus
10 to the power minus how
9
9 exactly. And picofarad? How?
10 to the power minus 12
10 to the power minus 12. So this is the basic unit. You have to, I think, lot of numerical paper you have already solved in circuit theory also. Okay. So you maybe use their microfarad, nanofarad, and picofarad. So how we can convert it to farad? For microfarad, 10 to the power minus 6, and nanofarad, 10 to the power 9, and picofarad, 10 to the power minus 6. Okay. So that we use in farad. We have to convert that one. So during the capacitor charging period, when the capacitor connected through a battery, so the capacitor is storing charge between the two plates, electrons on the left plate. Okay, that means here negative charge. And then this red symbol is indicated for the electrons, and this one white is a representation for the holes. Okay, so current is flowing from this positive polarity of the battery along this direction. So current flow from this side to this side, that means opposite of the electric current flow direction. Okay, so positively charged ion stored here on this plate, and negative charge stored on this plate. Okay, So the capacitor, that means storing a charge between two plates, this plate and this plate. These two are connected in parallel. So positive charge stored here. That means the movement of this hole from this side to this side, and movement of electron from this side to this side. Okay. So electric field created in the dielectric medium from this hole towards the electrode, that means positive plate to negative plate, okay, in the dielectric. So this is the direction of electric field, and the left plate are directed towards the positive terminal of the voltage source. Okay, so this leaves an excessive of the polarity charge holes. That means this white symbol represented by the holes. The electrons are pushed towards the right plate. Excess electrons have leave here negative charge. Okay. So negative charge will be placed here, since the electron movement from this to this, from this direction to this direction. So electron flow from this to this and again come back through this battery to this direction. Okay, this plate. So this leaves an excessive of polarity charge hole. So the electrons are pushed towards the right plate. Excess electrons leave a negative charge. So whenever your battery connected, that means you have to capacitor charge. That means the movement of electric current and the movement of flow of electrons and hole can be represented in the systematic diagram. Okay, during the charging period. Okay. So this is the use of capacitor when the both are showing when the charge through a battery, and when this capacitor is your charge, then you may be connected any load such like as a light here connected for the use of the capacitor for to supply the electric current. Okay, whatever the charge you have stored in this capacitor, you can be used for the supply of this bulb. Okay, so when the charging of capacitor is done by battery, and when your capacitor is charged, then during the discharging of capacitor is done when it is connected through a load. That means this capacitor behaves as a source for supply this load. That means bulb or any other loads you may be connected, okay, through this capacitor. So this is the charging and discharging of the capacitor. That means whatever charge or electrical energy you have stored in the capacitor, that can be used as a in electrical load, that means bulb here. Okay. So during that period, that means a discharge take place whatever energy you have to store in the capacitor. So this is the application of capacitor. That means whatever we have use here energy, that can be used. So this is the representation of the various type of capacitor we find out. That means ceramic disc type, monolithic ceramic types, and dipped silver mica. This is my layer, and solid titanium. So these are the various representation, and this is the axial electrolyte types of capacitor. I think you may find out this type of various capacitor in laboratory also for the practical purpose. Okay. So I think you may be seen in the either in your home also this type of capacitor you may be used. Okay. So we just try to find out the what is the total energy stored in the capacitor. So total energy stored in the capacitor, you have to suppose that we consider that the two plates. So one plate is a positive and negative. So potential difference between these two plates is represented by change in potential difference. That means delta V. Okay, whatever the potential difference between the positive and negative plates. So this positive plate charge is represented by plus Q and negative plate charge is represented by minus Q. So what is the small work done? That means the for the small movement of the charge stored and potential difference created between the two plates is delta V. So the work required for an external force to move a charge, that means a small charge is represented by dq. Okay, so small charge that is represented by dq. So here stored in the positive charge, that means positive ion, and here is negative ion. So through the potential difference is del v between these two plates, that means work done equal to voltage into charge. So a small charge that is represented by dq and a small potential difference that is represented by delta V. So as we know that Q equal to we can represent as C into V. That means capacitance into potential difference of the capacitor. That means potential difference is represented by for the small movement of the charge, that is delta V. So just find out here from this equation to delta V. This is the delta V equal to nothing but Q by C. So just put here value of dq and delta V, and just integrate total charge that will be stored nothing but the Q. Okay. So small work done, that means the delta V into dq. So delta V equal to nothing but how much? Q by C. Okay. So Q is the amount of charge on the capacitor at the time charge. So dq is being moved. So just total work done, if you want to find out, then just we have what we have to do here. That means we have to integrate from 0 to Q total charge. So total work done, we start with the 0 charge on the capacitor and end up with the total charge Q. Okay. So total work done, that is represented by W. So is nothing but 0 to Q into dW. So just put here the value of dW small work done. That means nothing but Q by C into dQ. तो इसको यदि हम लोग इंटीग्रेट करेंगे कितना आएगा वैल्यू? If we integrate this equation Q by C into dQ, and limit value is how much? 0 to Q total charge Q. So limit value is started from 0. Okay. So we consider that at the initial point no charge stored in the capacitor. Okay, means 0, and up to final total charge stored on the capacitor is Q. So limit, or you maybe say that the integration value from 0 to Q. So Q by C into dQ. इसको integrate करो कितना आएगा? Q by C into dQ. Integrate
Q square by 2.
Q square by 2.
Q square by 2C.
Just put the limit value, that means 0 to Q. So I think you are familiar with the integration, how you can put the lower limit and upper limit. Okay. So first we put the upper limit and minus lower limit. Okay. So upper limit is your Q. So just Q square, and lower limit is your 0. So minus total term is 0. Okay. So Q square by 2C is your total charge stored, that is work done required for the total charge Q stored in the capacitor. So this amount of energy can be stored in the capacitor. Okay. Your numerical value may be given, that charge value and capacitor value. Then you can find out in the numerical terms whatever the work done or energy we can stored in the capacitor. Okay, so this is the basic derivation for the energy stored in the capacitor. Okay, I think you are already familiar with this equation also. Is not? Hello.
Yes, sir.
This is the capacitor and inductor. You already familiar, I think. But we have to study here again. So just try to recap all this. So the work required to charge the capacitor is the amount of energy that you may be back to use when they discharge the capacitor. Okay. So because the electric force is conservative, so whatever the energy stored, that will be represented by U, and that will be again use that energy when the capacitor connected through a load. Okay, so that's the work required to charge the capacitor is equal to the potential energy stored in the capacitor, nothing but the potential energy of Q square by 2C, because capacitance value C and charge and potential are related through Q equal to CV. So you maybe simplify this equation again. Q equal to, if you see put that means CV. So from the numerator and denominator, one C is cancel out. If you put their value of Q equal to CV, so numerator part is nothing but C square into V square, and denominator part is 2C. So C is cancelled out from numerator and denominator. So only remaining part is your C V square by 2, and CB equal to again put. So you maybe put the charge either in stored in the charge and potential, or maybe charge and capacitor. So through this relation, you can be converted that one. Okay. So you have to keep in the mind the relation between the charge and capacitance value and potential, or maybe charge and in terms of capacitor. Okay. So either we maybe write for the Q square by 2C, or maybe QB by C, the same value. Okay. Next component is your magnetic energy stored in the inductor. Okay, so this is the representation, symbolic representation of the inductor, and physically you have to maybe in this way. So representation. So how we get magnetic energy stored in the inductor? Okay, so when the alternating current supply given to the inductor, then flux leakage, since the current is your alternating. So due to that flux linkage of the coil, EMF will be induced across this coil, and whatever the EMF induced, you may be later use as the source of energy that may be used for the supply purpose. So as you know that whatever the inductance value representation. So this is the nothing but the energy storage in the form of magnetic field and deliver when we required. This is the main our purpose. Whatever the energy is stored, we use when we required for that energy. Okay. So inductance is represented by change flux per unit current. That means 5 divided by current. So whenever the current passes through a conductor, that means the line of magnetic flux are generated. So due to that flux, the EMF will be induced. Okay. So this magnetic flux oppose any change in the current due to the induced EMF. So EMF induced is represented by small e, that means the instantaneous value, and their RMS value will be represented as capital E. Okay. So this magnetic flux upon any change in the current yeah. This magnetic flux upon any change in the current due to the induced EMF. So induced EMF is how we can represent that. There is a relation between the induced EMF and rate of change of current. So directly we can write here EMF induced is directly proportional to the rate of change of the current. Since the current is changing, alternating, so flux is also changing. That means we can say that the flux linkage in particular coil, so EMF will be induced. So EMF equal to directly proportional to the rate of change of flux or maybe current, maybe you want. So we just put here the value of EMF induced is directly proportional to the rate of change of current. That means di by dt. Okay. So this is your coil. In the sense that means you just supply given through this coil alternating current, and the flux direction you may find out. That means through this direction the flow of flux path. Okay, so that means the magnetic flux on this side to this side and this side to this side. So induced EMF. So what is the unit of inductance is Henry. So the opposition to the current is known as the inductance, and the component producing inductance is known as the inductor. So that the unit of inductance is Henry. So induced EMF right here directly proportional to the rate of change of current. If you remove the proportionality, so put some constant is the. So whatever the current changes in the coil, so EMF will be induced. So EMF induced, and that is represented by minus LDI by dt. That means opposite of the current. Okay. So EMF induced in the opposite of the flow of the current in the coil. According to the Lenge's law, you maybe know that the effect is always opposite the cause. So effect is here flow of current in the inductor, and the cause is your EMF induced in the inductor. So effect is always opposite the cause. That's why the negative sign, that means EMF induced is negative of the LDI by dt. Okay. So when we remove the proportionality, that means we have to put some constant, that is nothing but the inductance of the coil, that is represented by L. Okay. And di by dt is nothing but the rate of change of the current. So if you integrate this current, okay, then you will get the total EMF induced in the coil. Okay. So let's try to calculate this one. These are the representation of physical representation of the inductance. You may be winding such as put here in the form of inductance. Okay, these are the physical representation. How we can observe this inductance in the laboratory, or you may simply find wire on surrounding the core, or if you design any transformer, you may find out their winding how we can wound around the core. Okay, so this is the coil representation. That one. Okay. Next, we have to describe the inductance. Maybe two types: self-inductance and mutual inductance. So, what is the self-inductance and mutual inductance? So, the phenomenon in which a change in electric current in a circuit that produced induced electromotive force in the same segment, that is known as the self-inductance. So change in electric current, suppose that this one is your example of self-inductance. Whatever the current change in this coil and EMF induced in the same coil, that is known as the self-inductance. And the suppose that electric current change in this coil and EMF induced in this coil, another coil. Okay. So This is known as the mutual inductance. So EMF induced in this coil, that means another coil, due to the mutual inductance of this coil. Okay, and if the EMF induced in the self coil, if the current changes in this coil and EMF induced in the self coil, that is known as the self inductance. So this is the representation of self inductance and mutual inductance. That means through coil given with here supplied through a battery and one switch is shown here. So the current flow through this coil and EMF induced in the self coil. That means in this whatever the current change, so that is known as the self inductance, and current change in one coil and EMF induced in another coil, that is known as the mutual inductance. Okay. So the phenomenon in which a change in electric current in a circuit produce and induced electromotive force in the same circuit, that means the so self-inductance, and mutual inductance is nothing but it is defined as the property of the coil due to which it opposes the change of current in the other coil. Okay. So this is the classification of inductance, that means self-inductance and mutual inductance. We have to just so energy is stored in the inductor. Again, we have to same things follow as the energy stored in the capacitor. So here we already say that the EMF induced, that means voltage, is directly proportional to the rate of change of the current, but in the opposite direction. So negative sign is put here. So the EMF, induced EMF produced in a coil is directly proportional to the rate of change of current flowing through that coil. So voltage is directly proportional to the rate of negative of the rate of change of the current. So just remove this directly proportionality and put one constant, that is inductance value of the coil, and the work done equal to the, if you calculate the small work done, that means the small work done, that is represented by dq into v into small dq. That means for the I इक्वल टू क्या लिख सकते हैं हम लोग? की इक्वल टू लिख सकते हैं ना कि एक्चुअली करंट पर मिनट टाइम.
Yes, sir.
सो जस्ट वही वैल्यू यहाँ पे पुट करना है. डीक्यू को इस टर्म को हम लोग चार्ज के टर्म में रिप्रेजेंट करना है आई को. ओके, सो दैट विल बी रिप्रेजेंटेड एज डब्ल्यू इक्वल टू वी इंटू डीक्यू. सो डीक्यू को हम लोग जस्ट पुट करना है यहाँ पे वैल्यू टर्म्स ऑफ करंट एंड जस्ट इंटीग्रेट फ्रॉम 0 to so just to put their value, that means L into di by dt into dq. Okay, so dw, that means a small work done, so L into di by dt into dq. So di dq current is nothing but rate of change of the charge. Okay, so just dq by dt equal to, we can replace by I. So just I into how much? Di. So small work done can be represented as how much? कितना लिख सकते हैं इसको हम लोग? All work done, that means dw equal to L into dq by dt is nothing but I. Okay, so I into di. Okay, so just integrate this one, that means 0 to w total work done equal to L into integration of 0 to I into di. just इसको इंटीग्रेट करो, कितना आ रहा है वैल्यू? कितना आएगा? How much we will get? यहाँ पे dq by dt is equal to I. Okay, and integrate both sides of this equation. And limit value put just from 0 to I total correct. So how much you will get? कितना आ जाएगा? I into di. I square by 2.
I square by 2.
I square by 2. So total work done कितना हो जाएगा? 1 by 2 L I square. Is not? So energy stored in the inductor equal to 1 by 2 L I square. If you integrate this one. Okay. So if you put dq by dt equal to I and integrate both sides, so just repeat it in this form. So I di is nothing but I square by 2 and put there lower and upper limit. So 1 by 2 Li square total energy stored in the capacitor. Okay. So this is all about the energy storage in the electrical and magnetic energy in the capacitor and inductor. Okay. So just we stop here, and in the next class we will discuss another things. Okay. So
Yes, sir. Thank you, sir.
derivation is very easy. I think capacitor and inductor you already familiar and solve a lot of problem in the basic electrical circuit. So I think you may practice some formula again here. Okay. So we stop here, and in the next class we will discuss other things.
Okay, sir.